Hello. Hello, everybody. Good morning. So please have a seat. And those who have not collected the paper, you can collect it during the break. Okay. Right. So today we want to just leave it somewhere. Okay. We want to conclude our discussion of continuous random variables. And let me just go through some background first before we do something very exciting. Okay. So let me just recap some conditioning. All right. So we have a certain continuous random variable x, and it has probability density function f of x. So that's the PDF. Right. So now we are interested to understand the notion of conditional independence of x given an event A. So this particular event, let's say we assume that has probability bigger than 0. Otherwise, there are some things like this that don't make sense. But if the probability of A is bigger than 0, then we can define the conditional expectation of a random variable x given an event A in the following standard way, where this is the notion of the conditional PDF of x given A. Actually, just now during tutorial, we have done some examples on this, right? So I think people should be familiar. So the other notion that we should have in mind is the conditional expectation of a random variable given another random variable. Okay, this is given an event. And this is defined slightly differently, and it's as follows. You are taking the average over the conditional PDF. And here the conditional PDF is a random variable given another random variable. So this conditional PDF is defined to be the joint divided by the marginal, FYY. Okay, so this is slightly different as you can see from this, okay, because you are conditioning on different things. So now let us talk about a very important theorem, which I also examined you on the quiz, which is known as the total expectation theorem or the law of total probability or total expectation. That doesn't really matter. So here it says that if we've seen this many times in different forms, if A1 to AN form are events, let me make this clearer, are events that form a partition of the sample space, then we can adopt a divide and conquer approach to find the expectation. Okay, so you can sum over these constituent events, probability AI, and you can look at the expectation of x given AI, and we will see some examples of how we use this in a very short moment. Now, similarly, so this is analogous to expectation given an event. Now, we can also talk about the law of total probability or the law of total expectation when we condition on another random variable. So we can take the marginal over y, expectation value of x given y equals to y dy, and this integrates from here to there. So as you can see here, this part here is analogous to this, and this conditional expectation is analogous to this. This one, we are, let me drill home this point, we are conditioning on an event, and here we are conditioning on actually an event also. You can think of it because this is an event, but the book makes a distinction about this, and I think it's good. Here we're conditioning on another random variable. All right, so there are some slight changes in the definition, some slight differences in the definition, but as you can see, the essence is the same. You know, an integral is also like a sum, okay, in some sense. So you can replace this integral by the sum if you have all these events here that form a partition of the sample space. All right, so this is what we talked about last time. And actually, I wanted to go through an example to use all these definitions, which I will certainly do. But because all of you have put in so much effort to study for the quiz and you all did reasonably well, let me entertain you. I'm not going to sing a song, but let me do a particular example, okay? To illustrate the law of total expectation. Okay, example, but this is a discrete example, but I think it illustrates the point pretty well. So I have got two boxes, These are two identical boxes, and inside the boxes, you have money. And this box contains A dollars, and this box contains $2A. This is not typed out anywhere, it's not in the book, it's nowhere at all, okay? So of course you want the box with more, but you do not know which box has $2 or $2A, which box has A dollars. Okay, here is A is some number bigger than 1. You do not know which box has A dollars. You do not know which box has $2A because the boxes are closed. So the story is as follows. With probability 1/2, you pick box 1. Okay, this is box 1. Box 2. And of course, with probability 1/2, you pick box 2. Okay, so if you have taken my class, what is the expected amount of money that you earn? Expected, let's call the amount of money that you earn reward. What is the expected reward? With probability 1/2, you pick box 1. With you can just eyeball this, come on. Cheng Wei Xiao, not quite. With probability 1/2, you pick box 1. With probability 1/2, you pick box 2. Cheng Wei Xiao, not quite. 1.5A, yes. It is this guy, the second guy, yeah, 1.5A. Okay, so you know, when we go to casino and we have these boxes, we want to do better. Okay, so there is, and this is called the stay strategy. Because with probability 1/2, you pick this box and you must stay there. This is called the stay strategy. Okay, this strategy 1 gives you this. Now, I can propose another strategy. It's called the switch strategy. That means, okay, at the very beginning, you pick box 1, and definitely you switch to the next box. Okay, that seems like an illogical thing to do, because you may like box 1, but then you go and switch. All right, so under the switch strategy, what is the expected reward? Still the same, right? Still the same. You don't think it's the same? Because, okay, I pick box 1 with probability 1/2, which means that I don't pick box 1 with probability 1/2. So if I switch, I pick box 1 with still probability 1/2. I switch deterministically. That means I pick box 1 already. Okay, now I go to open box 2. Right, so what is my expected reward? 1/2, right? 1.5A. Right. Do you think you can do better than these two strategies, the stay strategy and the switch strategy? Yes, combine the two strategies together. How to combine? What is the rule to combine? Here's a suggestion, okay? We can do better. We can do better by $0.25 each time. Claim. There is a strategy that outperforms stay or switch by $0.25 each time. Very exciting, right? So what is this strategy? This is called a mixed strategy. This seems to be impossible because you have two boxes. It makes sense to just pick the box because you cannot see anything in the boxes. So the big strategy is the following, okay? First and foremost, you pick any box you like, okay? Now, you switch. Okay, so you pick any box, and you observe the money there. You observe the X dollars there. So X can be in A or 2A, right? X is in A or 2A. You either pick, but you do not know whether it's A or 2A. All right. You observe, you open the box, you observe. You observe the amount of money there. Do you switch? You open one of the boxes, you observe that there is $5 there. You can either keep it or you can switch to the next box. But if you switch to the next box, then you have to pick the amount of money there, which could be $2.5 or $10. Okay, so here's the deal. Suppose A is equal to 5, and then you pick this box here at the beginning. So now you can decide whether you should switch or not. You do not know whether, so here is 5. So here is either 2.5 or it is 10. Either half or double. Okay, so you observe X. Liao Xue, you understand? Okay, so now I will switch with probability . And I will stay with probability 1 minus 1 over X. So if I observe, so I open the first box, if I observe that the amount of money there is $5, I will switch with probability 20%. Okay. What's the intuition here? Why is this a reasonable rule? Let's look at the second line. Stay with probabilities 80%. So if the first box, if the box that I opened first has $100, a lot of money, so I will stay with probability 99%. I'm pretty happy. Okay, so I'll stay with probability 99%. And now I'll switch with a very small probability because there may be $200 the other side. Liao Xue, you understand this strategy? Huh? Yeah, if your amount of money is very large, if the amount of money that you saw originally is $100, then you stay with probability 1 minus 1 over 100, which is 99%. Yeah, so basically you observe the amount of money, then you flip a buyer's coin. And the bias on that coin is dependent on how much money you observe initially. Because this is the Vincent strategy. This is just one strategy that will do better. Let's prove that it does better by at least $0.25. Okay? So what is the expected reward under this strategy? Okay, let's see what is the expected reward under this strategy. Okay, so let's use the law of total expectation or total expectation. Okay, in order to do that, we have to define our events, right? Say A1, let's say A is enough. We pick the box with smaller amount of money initially. Okay. So A complement is we pick the box with the larger amount. So that forms a partition of the sample space. This by the way is called a 2-envelope problem. Pick the box with larger amount of money. Okay, so expected value of reward given A, or total reward is the following. And this two is half-half. That's simple. half, half. Right? Because we pick the boxes initially uniformly at random. Okay? So now we need to figure out these two things, which is maybe a bit more difficult. Let's think through it. All right? This guy here. What is the meaning of this? That means that we pick the box with the smaller amount of money, which is A. Okay? We pick the box with a smaller amount of money, which is A. So what is this? What is this quantity? Okay. So this, by the law of total expectation, it is switch, probability switch, given A, but that is independent, right? Probability expectation value of A, condition stay, probability of stay given A. Okay, but what is the rule? The rule is you switch with probability 1 over the amount of money they observe, which is A, because we are conditioning on the event that we pick the box with the smaller amount of money. So this one here is 1 over A. Okay, but then what is our reward if we do switch? Well, our reward is huge, 2A. Understand? So we switch with probability 1 over A because that's what we observe. Okay, what is the probability that we stay? Well, we stay with 1 minus 1 over A probability. And if we stay, how much money do we earn? A. Do you understand all these terms here? So this term here is, now we have the box with A dollars. So the rule, Vincent algorithm, is we switch with probability 1 over A. Okay, and then we are staying with probability 1 minus 1 over A. Now, if we stay, how much money do we earn? Okay, if we stay, we earn only A because that is what we are doing. All right. But if we switch, okay, how much money do we earn? Well, we're very happy because we saw the box with more money, which is 2A. Everyone understand this calculation? Everyone understand this calculation? Okay, so now we can do some algebra. This is A plus 1. Okay, after you do algebra. Okay, I'm not going to teach you how to do algebra. Okay, we can do one more thing. Okay, what does this mean? This means we pick the box with 2A dollars. Okay, then we can use a similar decomposition here. Expected value of reward given A, all right, A complement, switch, probability of switch. The conditioning here is not important because the switch does not depend on which box we chose. A complement stay, probability stay given A complement. So we can calculate this. Okay, now what is this? A complement means we pick the box with the larger amount of money, which is 2A. What is the probability that we switch according to my rule? Exactly, very good. 1 over 2A because, well, I wrote it here that we are picking the box with 2A dollars, right? Okay, now you switch. What amount of money do you get? A, you get less, so you are very unhappy here. Okay, plus now, I think you know that you stay with 1 minus 1 over 2A probability. So you need to multiply this by, okay, now you pick the box with the larger amount of money, but you're staying. So 2A. So let's see whether I can do this algebra here. So we have how much? Half minus, so 2A, this is half minus 1 is minus half, right? Okay, so it seems there's some asymmetry here already. Asymmetry is good. All right, so the total expected total reward from the law of total probability here. Okay, we just plug it in. Is this? So let's do a little bit of algebra. If we are not too scared of algebra, half plus 2A minus half times half. Okay, so 3A over 2. Let's write this as 1.5A because just now we wrote 1.5A. And then we have half minus a quarter, which is a quarter. So this is bigger than the stay or switch, pure stay or switch strategies. Oh, so randomization helps. So what have we learned here? That if we have a biased coin, we can actually beat the casino. Yes, David. Then okay, homework exercise for you. Can you do better than 1 quarter? Can you do better than 1 quarter beating the stay or switch strategies? David suggests use some other probability. I don't know because I have not done the calculation. But here the stay and the switch strategies give you 1.5A. So if my A is say $2, all right, then I earn a lot more, significantly more, because instead of $3, I earn $3.25 on average. Amazing, right? And the intuition for why this works is because if we had a lot of money initially, then we are very happy. We stay with a high probability. If we have $100 already, okay, we stay with 99% probability. So here, amazing, right? So you can do something, right? Yeah, so some people here in the Zoom are trying to calculate things. Good for them. So homework to you, not homework, but a fun exercise. How much better can you push this 1 quarter? Is 1 quarter the limit of, can you suggest another strategy to do better in 1 quarter? Over the pure strategies. These are called pure strategies, stay switch. Because you can only commit to one strategy. Whereas my strategy is a mixed strategy. Okay, anyway, this is just for fun. So I want in this lecture to illustrate some other of these things for fun, okay? But we will use some of the examples in the textbook, okay? So now Oliver, any questions? Okay, anyway, this is not typed anywhere, okay? So you either remember it or you take it down or whatever. I don't want to type this. Let's look at example, another example, which is problem 3.28 in the book, for us to illustrate the power of total probability theorem, okay? I want to go very slowly here. I want to go through a lot of examples that will help you. I don't want to go through material, I want to go through examples, okay? So now here we have this particular probability mass function, a probability density function, which looks like this PDF, 1 minus P lambda E to the lambda X. So this all looks very complicated, but if I draw a picture, it will become clear. So let's say P is 3/4, right? Let's say P is 3/4. Then what we have here for the red part is this decaying curve on the right-hand side. So this is our P lambda E to the minus lambda X. And then over on this side, what we have is this decaying curve over on this side. Okay, this needs to be a little bit lower. Okay, so this is 1 minus P, and that is P lambda. So basically, I just sketched this graph here. Okay, so this is our f of x and x. So now the question asks you to do the following. Okay, can you evaluate the expectation and the variance of this? Now, if you are good in integration, then you can easily go and find the expectation and the variance of this particular random variable. If you are good in integration, then you can just apply some formula. But we want to apply law of total expectation to this, okay? So we know that we don't want to do too much calculation. We know that if y is an exponential random variable with parameter lambda, then the expectation value of y is equal to lambda 1 over lambda. 1 over lambda. And the variance is also, the variance of y is 1 over lambda squared. And y is an exponential with parameter lambda means the following. Lambda e to the minus lambda y for y non-negative. So you see, the point I want to try to make here is that this x, right, and this y look very similar. So we had already done the hard work in doing integration by parts to figure out these statistics here, the expectation value and the variance. Can we leverage this and don't do too much calculation to get the expectation value and the variance of this more complicated random variable? This simple random variable only has support on the positive real line like this. But this random variable has support both sides, all over the real line. Okay, so it looks very difficult if we go and integrate this. But if we have some prior knowledge, and we have done this before for exponential random variables, we have this, then we can maybe make use of this to figure out the statistics of our x random variable. So it makes sense, actually, to define our event A to be the x non-negative. Okay, then event A complement is x negative. All right, then we have to figure out what is the probability of A. Okay, what is the chance that x is positive? Well, we can just integrate over 0 to infinity because that is the region of A, p lambda e to the minus lambda x dx. But this is p integral from 0 to infinity, lambda e to the minus lambda x dx. But we notice that this integral here is that of an exponential PDF. Exactly exponential. So this must integrate to 1. And so we get p. Okay, so that's the probability of A. The good thing is that it's positive. Let's say p is positive. Okay, so here is p is between 0 and 1, excluding 0 and 1. Okay, so with this knowledge, I claim that it's very easy for us to figure things out. Okay, what is the expectation value of x given the event A? All right. Now you notice that x has support left and right. But once we condition on x being non-negative, then we know from the property of the exponential PDF that f of x given ax is just an exponential on this side. Okay, this is very ugly. It's just an exponential on this side. And this one will be at lambda e to the minus lambda x, because we are conditioning on x being non-negative here. All right, because once we condition on the fact that we are non-negative, that x is nothing but a bona fide exponential random variable. So we know its expectation and variance very, very well, because this is 1 over lambda, and the variance of x conditioned on A, okay, is equal to 1 over lambda squared. So the second moment, which is variance of x given A plus expectation value of x given A quantity squared, that must be 2 over lambda squared. Okay, does that make sense? So this is quite tricky because condition on A, we are only looking at this part of the graph, this part. Okay, but as you know, and as I mentioned in tutorial, if you condition on A, then this whole thing gets scaled up. It gets scaled up by how much? You have to divide by the probability of A, but the probability of A is exactly P. So P here cancels with P here. And so you're left with this part here. This is exactly an exponential random variable. And we know its statistics very well. It's mean and variance. Okay, and so we know its mean and we know its variance. We know its second moment. The second moment will turn out to be useful very shortly. Does anyone understand this? Okay. Now, let us consider a slightly different event, which is A complement. Okay, so under A complement, what is our density, our probability density function? Well, I have to make space for the left-hand side because it will be happening on the left-hand side. All right, so it's a flipped exponential density, flipped over on the left-hand side. Okay, so here what we have, and I will make use of this, is that it's exactly an exponential random variable, lambda, but here is over on this side, so it's lambda e to the lambda x instead of minus x. That is our x given, f of x given a complement of x. Okay? Because I'm conditioning on the left-hand side now, a complement. A complement means the event that x is on the left-hand side. Okay, so what are its statistics? Well, the expectation of x given a complement. Well, if the expectation of this is 1 over lambda, by symmetry, the expectation must be 1 over lambda squared, or lambda, minus 1 over lambda. Now the variance is the same. The spread is also 1 over lambda squared. Because if I flip a random variable around the axis, the variance does not change. All right, you'll notice that the variance of, say, minus z is equal to minus 1 squared variance of z. So the variance z, which is the flip version of z, is the same as variance of z. That's what I'm using. All right, so now we can also compute the second moment, x squared given a complement, which is going to be the same thing, I guess. Yeah, 2 over lambda squared. Okay, so we started off with this particular strange random variable. But if we condition on this side, it becomes just an exponential random variable on the left-hand side. If we condition on this side, it's just a usual exponential random variable. And we are making use of the statistics that we know of the usual exponential random variable. So life becomes easy now because we can then compute the expectation of x by conditioning. Conditioning on a, probability of a, plus expectation of a, x condition of a complement, probability a complement. Okay, this is 2 over 1 over lambda times p plus minus 1 over lambda, which is the expectation of x given a complement, times 1 minus p. So that gives 2p minus 1 over lambda as desired. Now, does this make sense? Whenever we do some complicated calculation, we have to make sure that the answer makes sense. How can we check? Let's look at this picture. How can we check? We can check by particularizing the value of p to half. Then this whole thing becomes symmetric, right? If p is half, then this level is the same as this level, right? So this part here will be pushed up, and the p will be equal to half a lambda over 2 here. This part here will be pushed up, and then it will be symmetric around 0, and the mean will be exactly 0 if p is half. And in our answer here, if p is half, this 2p minus 1 is also 0. So all my constants are correct, as they should be. Understand? So in particular, if p is equal to half, then fx of x is symmetric around 0, which implies that the expectation of x should be equal to 0, which is corroborated by this expression and corroborated by our own very eyes, that if p is equal to half, the two curves are the reverse images or flip images of each other. You will have this and this, so the center of gravity must be here, right? Okay. So we can also evaluate the second moment by standard conditioning, all right, by law of total probability. This is usually called law of total probability. I don't know why this book uses a different name, but it's only slightly different. Square here, okay? But this is 2p over lambda squared because of the p here, and plus 1 minus p over lambda squared, which is 2 over lambda squared. So the variance, as all of you know, because all of you could reproduce this formula for me, which I'm very happy, the second moment minus the first moment quantity squared is 2 over lambda squared minus 2p minus 1 over lambda quantity squared. Okay, so you can simplify this or you can don't simplify this, but this is all the probability that we have done. We are not going to do arithmetic. Does that make sense? So if you do painful integration, you can get the same answer, and you can flip to the book problem 3.28. There are solutions there. You can go and follow their steps to do the painful integration, but we don't have to, because we notice that if we condition on a, this whole thing reduces to an exponential random variable over on this side. If we condition on A complement, this reduces to a flipped exponential random variable. And we know all the statistics of exponential random variables. So we are making use of those statistics to simplify our life via the law of total probability applied 2 times. Now, the law of total probability can be applied to x, of course, can be applied to x squared as well. You just have to change the x to x squared. And I'm just making use of all the statistics we have calculated. This is equal to p. This is equal to 1 minus p. And the second moments, you can obtain them from here. This is 2 over lambda. All right, this is this. And then the second moment of this, the second moment here is equal to 2 over lambda squared as well. So we are making use of it. We are plugging it into here. Okay. So hopefully it's not very difficult and it shows you the power of conditioning. This divide and conquer approach. We know how to do one thing. We know how to do another thing. We merge them together to get our final, more complicated expression. Understood? Okay. Can I move on? All right, so this is certainly simple enough to be examined in some exam. All right, so now I want to briefly talk about or remind you of the notion of independence of continuous random variables. It's very similar to the independence of discrete random variables we have seen before, but I just need to hammer home some points, okay? So we say that x and y are independent if they are PDF factorizers. So fxy, xy is equal to fxx, fyy for all values of x and y. Okay, so the only thing we need to check is this. But what are some of the implications of independence? Now, if x and y are independent, then many good things happen, right? If x and y are independent, we have that the expectation of the product of their product is equal to the product of their expectations. And it also holds that the expectation of the functions of the random variables is also equal to expectation of the individual functions. This can be checked, but we will not check these things. We will just assume them to be true. So if they are not independent, however, then the expectation need not be equal to the product of their expectations. This is easy, okay? This holds true for all functions f, sorry, I think I call it g and h. Okay? If x and y are independent, we have this property. And in particular, if x and y are independent, we can say some nice things about the variance. Okay? If x and y are independent, then I think Liao Xue asked me this before. Variance x plus y is variance x plus variance y. Okay. Now we don't need that x and y are independent for this to be true. You can have x and y be dependent and yet this still be true. But if x and y are independent, this is definitely true. You understand? So independence implies this, but not the other way around. Okay. So I think you also know that variance of say a times x is equal to a squared variance of x. So these two together tell us that for any constants a and b, variance of ax plus by is equal to a squared variance of x plus b squared variance of y. We can have this sort of property. I think this one people already know for a discrete case. The point here I'm trying to make is that it carries over to the continuous case. Is this clear? I think all of you know this because all of you asked me this sort of thing before, and this is in some tutorial as well, or in some homework as well. You make use of this to solve some equations. So I think all of you should know this. Okay, but if x and y are independent, you have this property. And why do you have this? The good students will ask why. We'll show this next time. All right. We'll show this next time when we talk about covariances. Any questions here? Any questions? questions? Okay, now I want to talk about the continuous base rule, and let's do an example. This is section 3.6, last section. The continuous base rule. But there's really nothing significant here about the notion of continuity. Okay, but this is a very, very useful tool if you want to go on to further classes that talk about statistical inference, probability, and statistics. So this is very important to know. If you want to do, for example, machine learning. Later on, I will talk to you about one particular example that is used very extensively in machine learning. Okay, this is not in the book. I typed this out. Okay, but what is the story here? You have a certain observation. You have a certain x, which is a random phenomenon, and it has a PDF f of x. So this is our random phenomenon. Okay, this random phenomenon could be the weather, all right, or rather the temperature now, the temperature. Okay, so the temperature in this room is a certain random number. It depends on whether we switch on the aircon, how many people are there in here, etc. But how do we know what is the temperature? We need to set up a measurement device. But that measurement device, Y, all right, may be noisy. Okay, so that measurement device may not be very accurate. It may introduce Gaussian noise. So suppose the temperature here is 25 degrees. But the measurement device, you see, oh, maybe 25.5 degrees, because there could be some noise. And that noise is imposed via a conditional probability density function. So Y here is our noisy measurement. Okay, given that we see our noisy measurement, what we want to do is we want to reconstruct our natural phenomenon. So we want to perform what is called in statistics as inference. Okay, we want to design based on Y a conditional map f of x given Y in order to figure out, in order to guess. So we want to guess the underlying value of x. Okay, we cannot see x, we can only see Y, because we don't really know what's the real temperature. We can only know the real temperature if we use a thermometer, but the thermometer say it's only like a 50-cent thermometer, is pretty bad. So that's maybe Y is our guess, but maybe you have some inkling that this thermometer is biased in some way. So you might want to undo the bias, and you might want to use an inference engine in order to understand what is the real value of x. For example, you may think, all right, for some reason, that your thermometer is always constantly adding 0.5 degrees to the measurement. Then you might want to reverse that. And the reversal is through this whole process of inference. Okay, and this is very theoretical, I understand, but we'll illustrate this through multiple examples. I also have a MATLAB demonstration. Okay, so how do we get this? We get this through the continuous base rule. And this is super important in other classes if you want to do machine learning. All right, there's this whole area of probabilistic machine learning that uses all these things. All right, something I teach also. F of x given y, x given y. This is something that we want because y is our observation and x is our random phenomenon. So based on the observation, you want to understand what is the spread, what is the PDF of the random phenomenon that you're after. So this is fxy, xy divided by fyy. But this can be written in another way, f of xx, f of y given x divided by the bottom. And the bottom can be written in this way as well. F of x t, we are integrating over t. I don't want to write x, dt. So this goes from minus infinity to infinity. So that's the continuous base rule, all right? But this is very abstract. So we have to illustrate this using some examples, okay? So the theory is actually not too much in this lecture, in these lectures, all right? And actually I spent a lot of time trying to do a lot of worked examples to illustrate the theory. And here's one worked example. Okay, this is very similar to the book. But because some students in the class say that the book is very Americanized, right? Like Dong, right? This guy, but he doesn't show up. He says that the book is very Americanized. So let me make the example NUS example, okay? But it's similar to the example in the book. The waiting time of 95. I always say 95 because I take 95. Is exponential random variable y. Okay, so you go to the bus stop and you have to wait y minutes to get onto 95. You only want to get on 95. However, the rate parameter of the exponential random variable, which is the lambda of the waiting time y, is another random variable x, and this x is uniformly distributed in the interval 1-3 minutes. Okay, so a few things first, all right? A few things first. So f of y given x. Okay, before that, right? So what is our density of x? X is uniform. Uniform on 1-3, so it's 1/2. All right, x between 1-3. Okay, that is our rate parameter. That is x, 0 otherwise. Okay, now we are given that our waiting time conditioned on the rate parameter being x is exponential lambda or exponential x. Okay, so this is the equal to x e to the e to the y this way 0 for y greater than or equal to 0 and else. Now this looks very strange, right? But you recall that for an exponential random variable with parameter lambda, fy of y is equal to lambda e to the minus lambda y bigger than 0, 0 otherwise. So now our rate parameter, which is our lambda parameter, is a random variable and we call it x. Okay, we call it x. So this lambda becomes x here. So there are a lot of things happening, but here lambda becomes x. But the x itself is random. You do not know whether it's 1 or 3. Usually when we talk about random variables, I tell you, oh, the rate of the exponential distribution here is 1. But here, the rate actually is itself uniform. So there are multiple layers of randomness. First, the rate parameter of the exponential PDF is a uniform random variable on 1-3. And the amount of time you wait is an exponential random variable whose parameter is uniform, is random. So what do you expect? Before we do anything, right? What do we expect? Suppose we observe y equals to y. Okay. What is the conditional PDF in this case? Conditional PDF of x. Okay, so what do you think before we do anything? Okay, so before we do that, let me remind you that the expectation of y given x equals to x is 1/x. We have already seen for exponential random variables that the expectation is 1 over the parameter lambda. But here lambda is called x, okay? So it's 1/x. All right. So suppose we went to the bus stop and we waited 5 minutes. We waited 5 minutes. That's certainly possible because f of y given x is exponential random variable. It takes on values on the positive real line. That means all positive real numbers. Okay. The rate is from 1 to 3. Okay. Suppose we waited for 5 minutes. How does it change our belief about x? Initially, x was uniformly distributed. Okay. Initially, x was like that. Fx of x was 1 to 3, uniformly distributed. 1/2. Initially. But now we observe y equals to y. What changes? All right. So we can just apply the continuous base rule. F of x given y, x given y is equal to f of y given x, y given x, fx of x divided by the normalization constant, which is just the bottom part here. I'll just be lazy and copy. Okay, so we can plug everything in and we can see what happens. Okay, so let's plug everything in. So this is gonna be, okay, x e to the minus yx times half divided by integral from, well, we don't need to go from minus infinity to infinity because the support of x is from 1 to 3 only. And this is half. The half and half can cancel. T e to the minus yt dt. And so the half and a half can cancel. You're left with this divided by the bottom part, which is 1 to 3 t e to the minus yt. But this expression is only valid for x between 1 to 3. Because x can only range from 1 to 3. This example is the same as the one in the book, but the one in the book is more Americanized. Okay, so what does it say? All right, so this is our final expression. Is it very illuminating? It's a bit confusing, right? Because there are no pictures in the book. So I graphed this yesterday. Okay, so let us take a look at what's happening here. Okay. Right, so let's look at this. Suppose I know that y is equal to 2. All right, hang on. Suppose I know that y is equal to 2, right, which is here. Is it big enough? No. Suppose I know that I observe that y is equal to 2. All right, then I'm plotting this expression here. I'm plotting f of x given y, x given y is equal to y. All right, I'm plotting this. And this can only exist, right, from 1 to 3. So I'm plotting this function here. I do numerical integration to figure out the bottom. Okay, so there's this shift. Initially our density of x is uniform from 1 to 3 with value half. But if y is equal to 2, that's the blue line. You see that there is a shift of the density towards points that are closer to 1. Why is that the case? That is our new belief about the value of x. All right, so this is actually f of x given y, x given y. Now, if y is equal to 2, that means that, all right, that means that if you look at this expression here, this mean here, what does it tell us about the value of x? What is x likely to be? Okay. So suppose y is equal to 2. Then this part is about 2. So x is about half. Right? Because that part I observe that y is equal to 2, so the expectation is about 2. And I equate 2 to half, 2 to 1 over x. I get x is about half. So my belief about x is actually half, but x is between 1 and 3. So most of the belief will be shifted to the front. Okay, because I observed that y is equal to 2. So this quantity here is about 2, is 2. And so my belief about x is that x should be about half. But x cannot be half because x must be between 1 and 3. So all the mass gets shifted closer to 1, because that will make x being equal to half more likely in some sense. Now, if we change our observation, say we observe and we went to the bus stop and we observe that y is equal to, say, 1/5. Okay, that is the red line here. Then this becomes, okay, this becomes about 1/5, which means x is about 5. Again, the x here is outside the range of 1 to 3. So actually, what we see here is that is this line here. There's some shift towards the right-hand side. There's some shift of the belief of x from a uniform, it just shifts to the right-hand side. Okay, so that is for y equals to 1/5. The book doesn't do a very good job of explaining this. Suppose y is equal to the remaining one, which is 1/2. Okay, the remaining option here that I drew. Then this is about 1/2 on the left-hand side. So x is about 2, which is right smack in the middle of the interval. So it reinforces that x is around the middle of the interval 1 to 3. And that's why we observe this very interesting hump here. We observe this very interesting hump. It somehow reinforces the belief that x should be around the middle of the interval. Okay, so this is the meaning behind statistical inference. If you take those statistics classes, all right, they will make use of the continuous base rule all the time. The point here is that we have an unknown parameter, x. We observe x through a particular conditional probability density function. Now, if we observe y, that alters or changes our belief about x. How does it change? Now, if y is such that x, we believe that x is in the middle, then it changes from x being flat to x being like a hump here, because it reinforces the belief that x is in the middle. But if y is, say, 2, which means that x is going to be half, all right, x is half, then x is somewhere here, which means that we must significantly bias our belief about x. And conversely, if y is 1/5, that means that x is about 5, right? Which means that it will bias our belief to the right-hand side of this interval. Okay, so this is a bit the first. If you see this the first time, all right, this, I must tell you, is a little bit hard to grasp. But this is the example that is provided. I will provide one more example to illustrate this point after the break. Okay, so I will see you at 3:08 after the break. Okay, see you. Can you come down and talk to me? Yes, the area in the graph is all 1 because right, when I drew this, I also computed the denominator here. This denominator serves to normalize this. So originally, right, the graph without any measurement, without any y, it is at here. Okay, it's half. But if you observe one value of y, it changes your belief about x. All right. No, this is not quite correct. Yeah. I do give method marks for things that I find quite meaningful. Yeah. You should put in numbers. That's the whole point. It's harder than this. Yeah. Here I try to make it a bit easier. You should do all the problems that are meaningful. So next week, we will have, of course, lecture on Tuesday. But Tuesday, I will ask my student to do it. She is very nice. Because she's going to be professor, so I need to give her some training. I will also be here, okay? Be nice to her. But also ask her questions, all right? All right, let's resume. Okay, everyone, hello, please settle down. Let's resume. If you want to talk to me about adding a 0.5 bucks, 0.5 bucks, I'm happy to entertain later on, okay? Now, so now let me give you another example. That example was from the book. I find that it's too difficult. So let me give you a very simple coin toss example of the continuous base rule or just base rule. So there is a coin toss that is modeled as a Bernoulli random variable. Okay, so this is half of a base rule that is continuous and half of it is discrete. So a coin toss y is modeled as a Bernoulli random variable. Y equals to 1 means heads, y equals to 0 means tails. But y itself is Bernoulli with the probability being of 1, probability that y is 1 is a random variable x, which is uniform. Okay, so before the whole experiment starts, before you toss the coin, a genie picks a certain number x from the unit interval and fixes that to be the bias of your coin. So for example, Wicked came and told me that x is equal to 0.3. Then my coin's bias, that means the probability of y being equal to 1, is 0.3. And how did Wicked choose 0.3? He randomly sampled a number from the unit interval 0, 1. So he used MATLAB to generate a number between 0 and 1 and say that, okay, that is the bias of the coin. And then I will play the coin experiment. Okay, so now x is, of course, as I mentioned, uniform originally on 0, 1. Okay. But now I observe two y's. I observe that y1, okay, is equal to 1, and y2 is also equal to 1. All right. Now, how does that bias my belief about the, how does that change my belief about the coin's probability density function? Initially, it was uniform on 0, 1. So initially it was like this. But then I realized after I tossed the coin, right? That's the initial probability density function of x. Initially, that was the probability density function of x that we get generated x from. And then I tossed the coin 2 times. And then I saw 1, 1. Actually, this gives us some idea about what x is, right? It's quite likely that x is biased towards the right-hand side. All right, so I would expect something like, okay, after I do the calculations, actually there will be some biasing to the right-hand side, like this. That means there's less probability that x is small and more probability that x is large. Do you think so? If I observe these things? And then if I observe, say, ... y 100 equals to 1, all ones. Oh, then there is a very strong idea that maybe this is super steep, like that. There's a lot of mass concentrated at 1, because there's very strong evidence that the coin's bias is very much close to 1. Can we make this precise? Understand? Okay. So here we are making use of the continuous base rule. Instead of doing too many, I will only do y1 equals to 1 and y2 equals to 1. Okay. Now, first and foremost, okay, the question is, now, if we observe this, what's the conditional? And the word conditional is key because this is the marginal, the original or the marginal. What's the conditional? PDF of x given that y1 is equal to y2 is equal to 1. That biases our belief that x is on the right-hand side. Can we make that precise? Okay, before we start anything, let us do a little bit of preparation. Okay, for a Bernoulli random variable, okay, for a Bernoulli random variable y with bias. Bias means the probability of 1. Bias x, okay, x equals to x. Bias means probability y equals to 1, okay, of the bias, okay. For Bernoulli random variable y with bias x equals to x, its PMF is given by the following: x power y, 1 minus x power 1 minus y, where y is between is 0 or 1. Now, usually we write binomial PMF as the following: P of y given x, y given x, that is equal to 1, or that is equal to x and 1 minus x. When y is equal to 0, when I is equal to 1, and y is equal to 0. That is our probability of success, or the bias probability. So when y equals to 1, you plug it inside here. You see that you recover x to the power 1, which is this. And this part is 1 minus 1 is 0, so this part gets killed. You are left with this. Okay? And similarly, if y is equal to 0, then this guy gets killed, and you're left with 1 minus x here. Okay, so this way is a very convenient way of writing a binomial or Bernoulli random variable. A Bernoulli random variable. Okay, we just use these exponents to get rid of the part that we don't want. Okay, so now we can actually answer the question. All right, we would like the density or the probability density of x given y1, y2, x when y1 is 1 and y2 is 1. Okay, so that is nothing but the probability mass function of y1, y2 given x, y1, y2 given x, fx of x divided by a normalizing constant, which is the integral from 0 to 1. This is just an application of the continuous base rule. y1, y2 given t, f of x t dt. This is just base rule. Now, we assume that given x, the tosses are conditionally independent. So what this means is that the top here is x to the power y1, 1 minus x to the power 1 minus y1, x power y2, 1 minus x power y2, divided by the integral from 0 to 1, this times 1, because fxx is 1. T to the y1, 1 minus t to the y1 minus y1, t to the y2, 1 minus t to the 1 minus y2 dt. But y1, y2 are equal to 1, 1 respectively. So this becomes x squared at the top, because y1 is 1. So this gets killed. And this is 1 minus y2. So this gets killed as well. So you're left with x to the power 1, x to the power 1, which is x to the power 2. And the bottom as well, 0 to 1 t squared dt. And if you carry out this integration, this is 6. Oh, no, I cannot carry it out. This is 3x squared for x between 0 and 1. So initially, our density of x, or probability density function of x, is the following. Based on the prior, okay, x was uniform on 0, 1. Okay, that was f of x, 0, 1. That was the original density. But after we observe that y1 is 1 and y2 is 1, that really biases our belief that x should be on the right hand side. And the precise formula is this. How do you draw this graph? Well, it's a quadratic, and at 1 it is 3. So you go up like that. So indeed, after you observe 2 1s, most of the mass gets concentrated to the right hand side. Most of the mass gets concentrated on the right hand side, and you believe that actually x is closer to 1. So initially, before you toss anything, all right, x is uniformly distributed on 0, 1. But after you gain some evidence, y1 equals to 1, y2 equals to 1, then your belief changes after you perform the calculation. Now, I'm going to do one more. Suppose now your realization is the following. Y1 is equal to 0. What do I do? Y1 is 1. And Y2 is equal to 0. Now, what do you believe? So we can actually sample a number x from 0, 1, and the coin's bias is now little x. Then I toss the coin 2 times and I get head tail. What does that reinforce my belief of the x to be? You think it's like this. Can we prove that it's like this? Okay, because now what do we believe in? We believe in x being stuck in the middle, concentrated at half. Do you believe that? So let's try to show that, okay? In this case here, well, we can use the same formula. I don't need to rewrite too much. All this is the same. Okay, in this case here, we can run base rule in the same way, but now y2 is equal to 0. So what do we set here? This is equal to 1. This is gone. This is gone. And this is equal to 1. All right, and so what we are left with is basically x1 minus x divided by integral from 0 to 1 t1 minus t dt. And if you carry this out, I'm not going to do this. I'm not going to do this integration. You get 6x1 minus x, where x ranges from 0 to 1. So what do we have? Do we have the intuition that Liao Xue tells us? Okay, so initially our belief was this, that x is between 0 and 1 uniform at random. Okay, that's fxx. But now, after I saw y1 equals to 1, y2 equals to 0, your intuition is that there's a hump in the middle. So what is this curve here? Okay, this curve is a hump in the middle, and the hump, 3/2. So here, this is not a very nice picture, but here is 3/2. Middle here is half, 3/2. This one is our f of x given y1, y2, x given 1, 0. Does that make sense? So we actually show your intuition is correct, that there's a hump in the middle. If there is 1, 1 and 1, 0, because it reinforces our belief that x is in the middle. This is the use of inference and continuous base rule. The first time you listen to this, no matter how good the teacher is, you'll be confused. Yep. Okay, or no matter how bad the teacher is, I'm trying my best. Okay, so here it reinforces the belief that you are in the middle, because y1 is 1, y2 is 0. So homework, I have written this up, I've latexed this, all right? You can actually try, what's the last thing to try? y1 equals to y2 equals to 0. What do you expect? All right, well, we expect this. Okay, I expect something like this. I expect to be biased in the other way, because now we get 2 tails as our outcome. So the probability of heads will be kind of small. So I will expect this. This is 3 here. Can you prove that this is true? Okay, this is f of x given y1, y2, x given 0, 0. So we believe that x is actually concentrated close to 0, but we're not discounting the possibility that x is still close to 1. It's just that we push the belief to the left-hand side. Can you do this calculation by yourself? Okay. It's the same thing. Okay, you just have to notice which part gets killed here. Is that clear? Let me repeat myself. What's the story? Now, we have 2 coins, all right? We have one coin. We're going to toss it 2 times. But the bias is not known. The bias is originally a uniform random variable in the interval 0, 1. Okay, so that is our original bias. Okay, we're going to pick a certain value. Say we pick this value here, or very close to 1. Then it's very likely that the 2 tosses that I get are going to be head-heads, right? Suppose we get sampled the number 0.99. All right, it's very likely to be head-head. But we cannot discount the possibility of tail also. However, if we saw head, that biases our belief of x to be very close to 1. Can we make that precise? And we make that precise through using continuous base rule, which is this formula here. Okay, it looks a bit complicated, but this is the formula. This is the formula. You have to flip the y's around and you have to keep the x there, flip it around, and then here is the bottom is the summation or the integration of the top. Okay, so the first thing to notice is that for a Bernoulli random variable, we can express its probability mass function in this strange way. But this reduces to the usual case if we particularize y to 0 and 1 respectively. Okay, then we recover the probability, which is x. Okay, so now if we observe 1, 1, then what gets killed? All right, this part gets killed, this part gets killed, this killed, this killed. Then we are left with x squared because you have x power 1, y2 power 1, x squared. The bottom is t squared. So after you perform the integration, you get 3x squared. You can plot this and you see this. There's a concentration to the right-hand side. All right. Now, if you get heads, tails, then you can perform the same game and you will get this expression at the very end. So if you get heads, tails, your belief gets concentrated to the middle. There's more mass in the middle than originally. Okay. Now, if you do this, you have 2 tails, then it's obviously the opposite direction. Now, this is a very simple fact. Or maybe you don't find it simple, but if you absorb this for a little while, it turns out to be very natural. This is very important in this fact. It's very important in statistical machine learning, something I also teach later on. Okay, so this is very important if you ever want to do something theoretical. And even not theoretical, this is used all the time. Really used all the time. So one has to know it. Okay. So that is another example of using base rule or the continuous version of base rule. Now let me conclude by talking about inference of a discrete variable from a continuous variable. And we will conclude with a certain example as well. Discrete variable. Okay. So x is discrete, is a discrete random variable, and y is a continuous random variable observed via x. So the probability that x is equal to x condition on y is equal to y is continuous, okay? We express x as a PMF and y as a conditional PDF and divide by the normalizing constant, which is, we divide by the sum because x is discrete of px x prime f of y given x prime. So that is the base rule when what you are trying to guess x is discrete. What you observe is continuous. Okay, so the only way that one can internalize this sort of formulas is via examples. All right, example. Okay. So we have a signal. I think communications, they like to talk about these things, all right? We have a signal that we want to send S, and this signal is a BPSK. I think it's called BPSK, but I don't really know this. S is either -1 or +1, okay? Either -1 or +1 is transmitted through a Gaussian channel. You heard of that, okay? So a priori, at the very beginning, we want to transmit 1 with probability P, and we want to transmit -1 with probability 1 minus P, say P in 0, 1. Okay, so we have a signal that we want to transmit across a noisy channel, and the probability that the signal is actually 1 is P. -1 is 1 minus P. Okay, now what do we see? We receive not S, but we receive Y equals to S plus N. N is noise. N is basically Gaussian noise, standard Gaussian noise with mean 0 and variance 1. Okay, so the question is, what's the probability? What's the probability of S equals to 1 given we observe Y equals to Y? Okay, and we are going to sweep through all values of Y and we're going to see whether it makes sense or not later on. So the picture is the following, and we need to draw a picture. Okay, so we either transmit S equals to 1 or S equals to minus 1. And this is the Y. Okay, and this is F of, and I'm not going to draw this. Okay, so what is the conditional probability density function of Y given that S is equal to 1? Now, if S is equal to 1, all right, if S equals to 1, then Y is Gaussian with mean 1 and variance 1. The variance does not change if I add a fixed number to it. Okay, so let me put this here. If S is equal to 1, Y is Gaussian with mean 1 because S is 1 here. This has 0 mean. So the mean of the Y must be the mean of S because this guy has 0 mean. Now, if I add a fixed number to a Gaussian random variable, then the variance does not change. Okay, the variance does not change. So the variance is still 1. So at this point, I can draw the probability density function of Y given that S is equal to 1. It's Gaussian. So that is that. Okay. Now, clearly, this is very symmetric, right? Now, if S is equal to minus 1, then Y is certainly Gaussian with mean minus 1 and variance 1. Let's copy on this side. Mean minus 1 and variance 1. So we can draw the density. This way as well. So that is the probability density of Y given that S is equal to minus 1. So as you can see, it's symmetric here. Okay. So what we want, so let's write down a few expressions first. So f of y given s, y given s is equal to 1 is basically a Gaussian with mean equal to 1. So you have y minus 1 squared over 2. The variance is still 1. Okay, so that is the density of a Gaussian with mean 1 and variance 1. And if s is equal to minus 1, then this is plus. That's all. So these two are the equations of these curves here. This is this, and then this one here corresponds to the red curve here. Is that clear? Okay, I see some nods. I see some completely. Actually, I've done this sort of thing before, maybe about 1 or 2 weeks ago. So we are interested now in the question, okay, what's the probability of s equals to 1 given that we observe y equals to y? What is your intuition? All right, suppose I observe that y is here. What is the probability that s equals to 1? Pretty large, right? Because I have very strong evidence that s is equal to 1 if it's here. It's very unlikely that I am associated to the red curve if y is here, I observe here. Okay? Now, similarly, if y is over there, then it's very likely that s is equal to minus 1 because this is closer to here. Now, if I observe that y is equal to 0, now, then, well, you are equally undecided. All right, so let's try to make this precise. Okay, so we try to make this precise as follows. Probability that s equals to 1 given y equals to y is equal to p of s1 f of y given s. We need to know what is discrete and what is continuous. The discrete things we use p, the continuous things we use f, divided by, okay, p of s1 fy given s y given 1 plus p of s minus 1 f of y given s y given minus 1. Okay, so we put everything in nicely. So what we have is the following. P of S1, the probability that S is equal to 1 is P. It comes from here. So we can plug it in. Right, P. And the density of Y given S is equal to 1 is 1 over square root 2 pi e to the minus Y minus 1 quantity squared over 2. Okay. So we can do the same at the bottom. All right. So we have this part here, plus we have this part here. But here we need to change this a little bit to be 1 minus P, and this is a plus. Okay, this looks very complicated, but actually it can be simplified. And the simplified expression is PE to the Y divided by PE to the Y plus 1 minus PE to the minus Y. Only the linear part gets retained. Okay, I'm not going to do all the simplification. So does this actually corroborate our intuition? So if say P is equal to half, so a lot of things can cancel. And in particular, the P and the 1 minus P can cancel. Then the probability S is equal to 1 given Y is equal to Y is E to the power Y divided by E to the power Y plus E to the power minus Y, which can be written as 1 over 1 plus E to the power minus 2Y. Now, if you look at this picture, and I will copy this picture again. If you look at this picture carefully, and you take Y to be something very large, say 3. Now, then this is very close to 1, right? Okay, so let me make a remark. If Y is large, E to the minus 2Y is small. And the probability that S is equal to 1 given Y equals to Y is close to 1, as expected, as our intuition expects. Conversely, if Y is small or very negative, remark, if Y is very negative, then E to the minus Y is large. And the probability that S is equal to 1 is close to 0 as expected. So if I observe that Y is here, what's the chance that S is 1? Very small, because the chance that S is minus 1 is very large. Okay? Since here you are strongly believing that actually this came from this density. Now, the final remark is that if Y is close to 0, let's say it's exactly 0, then this guy is 1. E to the power 0, anything is 1. Then probability S equals to 1 given Y equals to Y is half, as expected. Okay? Now, if you are here, right in the middle, the probability that you come from here or the probability that you come from here is half, as symmetry suggests. So today we have seen many uses of continuous base rule, discrete base rule, and so on. And this actually forms a basis for many other classes in future. All right, if you ever go down the signal processing control or machine intelligence track here in EC, I think that's what they call it. Okay, so as you can see here, we are just basically flipping things around. All right, we have this conditional probability density function. We have the prior probability that S is 1 or S is minus 1. And we would like the probability that S is 1 given that I observe something. Okay? And if I observe Y to be far out here, it's very likely that S is 1. And that is corroborated by the formula. I hope that you get at least something that I'm trying to say. But in case you don't, we have a lot of opportunities to practice these things. Okay? At least for that coin toss example, I typed out something, but I just realized that there are several typos. I will fix those things. Okay? I typed that very quickly, like in 5 minutes last night, when I was deciding, is there a better example than the silly example in the book that is too difficult to explain? But nevertheless, I explained it. So actually, this brings us to the end of chapter 3 of the book. The main chapters are chapter 2 and 3. And next time, Tuesday, we will start on chapter 4, the derived distributions. That means if I give you a particular distribution or a particular probability mass function or probability density function, and I apply a certain function to the random variable, what is the new probability mass function or the new probability density function? So we want to transform a random variable from something to something else. And can we transform its probability density function? That is what my student will try to explain to you. And let's see how she performs. She has actually helped me teach my graduate class before, so she's quite reliable. Okay. So I will be here in case she messes up, right? Right, so that's all for now. Today we can stop a little bit early. Thank you very much for your kind attention. And in case you want to ask me questions, there will be office hours tomorrow at 4 o'clock as usual. I don't know whether I should go through the quiz or not, but maybe I will just do a small, if you turn up for office hours tomorrow, I will explain question 3. I won't explain question 1 and 2, not necessary, because most people got 1 and 2. Okay? If you want, you can show up for office hours. I will go through question 3, and then you can ask me other questions. Okay? Thank you very much.